This part of the series will focus on taking the audio descriptor analysis that we did in the previous tutorial, expanding on it, and creating the actual visual space that we will explore.
To begin with, I'm going to simplify a little bit of this patching that we did because it's going to make our analysis a little bit more readable, a bit easier to come back to in the future. And we also get to learn about one of the, features or interfaces of these descriptor objects. So just to recap very briefly, we extract the loudness and the peak amplitude here from this object in a 2-channel buffer. We then extract just the loudness into this buffer, which we then calculate the stats on, which we turn into a list, which we then extract a specific index from. In this case, because we're taking the 6th index, we're getting the median here, or the middle value. We can reduce the amount of times we need to poke in and out of buffers here by using an attribute called select. And this lets us select in a kind of human way what we want to extract from a buffer without having to go through buff select. In this case, we just want this first channel, which is the loudness. And we can check what select expects by having a look at the default values. So we can choose from loudness or peak. So if I do @select loudness, and I just do some analysis here, you can see instead of having a 2-channel buffer to begin with, we just have a single channel and it contains the loudness, meaning we can entirely get rid of this buff select and go straight into the stats. We can also do the same thing here for buff stats. So I can say @select mid, or middle value, or which by default is the median. And if I do the analysis again, it's a little hard to see, but we should have one singular value in dB stats. And I've made a little mistake. We need to set the source here now to loudness because we're no longer looking at an intermediate buffer here that extracts only that first channel for us. So I'll hit this again. And you can see here we have a single value rather than 7. And so I don't actually need this ZOnth anymore. I can just go straight out. It's a single item buffer. And we can always change this. So I could say mean. Now we have the mean instead. The skewness. And this is I guess a simpler way of doing it, but it's also a little bit more human readable, which is nice for making self-documenting code and also cutting down on the number of buffers that we need to make and maintain and track. So in this next bit, we actually won't need any of this looking up and grouping and sorting. So I'll get rid of that as well. And I'll remove this. And we won't actually need a buff to list there. So I've really boiled down the analysis chain into its most salient and minimal parts. If I just move this over a bit. All I need to do now to add a second descriptor to this analysis is copy this. If I just shift my patch over and connect up all the various bits. so the start frame and the num frames, to tell it which portion of the buffer to analyze. If I route these for neatness. Now we have two sides of the patch here, which will produce one number each, helping us towards this idea of building a kind of coordinate system out of audio descriptors. But at the moment, this just does the same thing, fluid buff loudness and fluid buff loudness. So I'm going to change this to buff spectral shape. And I'm going to give it proper buffer name to put the data that it makes into. So I'm going to call it spec shape. And we're also going to take the stats again. So I need to change the source to spec shape and change this to spec stats. Now, if I just attach buff to list, I also need to change my output buffer, and select loudness actually no longer is the right kind of thing that we need because we're dealing with spectral shape. And so you can see here, we're getting a value out, but we haven't really done all of the things that we need to. If I look here, spectral shape actually gives us a 7-channel buffer. Much like loudness gave us a 2-channel buffer. Well, in this case, 0 because we've done select, but by default, it gives us the loudness and the peak amplitudes. So spectral shape is similar. It gives us 7 different spectral shape descriptors. And I always remind myself by going to the reference what these are, which are described here. I actually just want the first one, which is the spectral centroid. And so again, we can use the select parameter to just get what we want. And these are the options. So if I do @select centroid, and have a look in here, I may not have done my job entirely right. Exactly. So it's always important to set the inputs and outputs to be the right thing. Have a look. There we are. There's a single value. So in this case, it's going to be here, this value describing the median spectral centroid of each segment. And it's good to know now that select is not like a picker, in that if we were to do something like, if I have a look back at my list here, roll off here and centroid here. If I do that and look in spectral shape, we get 2 channels. So the first one here is centroid, and then the second one will be roll off. If we did this, roll off centroid, and I reprocessed, you won't actually be able to see it, but we have the exact same result as if we did centroid roll off. So in other words, roll off centroid is exactly the same as centroid roll off. The reason for that is select is a mask, not a cherry picker. It doesn't extract specific things in the order that you specify them. Rather, it's more like a filter. It says these things are allowed to pass through at the output. So if I do that, it's actually, we only see one thing anyway. But when you combine it with multiple select choices, you need to be aware that you always get the same order of things out. That doesn't affect us directly here, but it's a good tidbit to know. So if I get both of these values out. And set this to be right. Great. And what I'll do to preempt the next part is join these values to make a new list that is 2 elements long. And actually, again, I'll just keep making space as I go because we're going to need it. And I make a buffer called point adder, which is going to be 2 samples, right? Because we have 1 point here, so 1 sample here and 1 sample here. And we use list to buff at destination point adder. Every segment that we analyze goes into this buffer. So we're actually just seeing the last one here, but it makes sense, right? This first channel is a very, very negative value, the dBs, and the second channel is a very, very positive value because it's the spectral centroid in hertz. And this is important because what comes next is that we start adding these points to an object we haven't seen yet called the fluid dataset. And the fluid dataset is a kind of generic data container that talks to lots of FluCoMa objects for when we want to do something to do with machine learning, or perhaps storing this data to be loaded elsewhere. It's a bit like a call in a dictionary, in that we can give it a name and use it in different parts of the patch, but it really forms the fundamental basis of shuffling data and processing it in the FluCoMa universe. So if I make one here and call it analysis, we'll work backwards. So the way that we add a point is with this message. And again, I keep doing this, but space is really, really limited. So I'm just going to take this and move it up here because it makes a little more sense when we keep things vertical. So every time we get a point of analysis in this buffer called point adder, I want to add it to the data set. And we use the add point message with a variable here or something that we can dynamically change, and the name of a buffer containing some data. So in this case, point adder. And you'll see here, if I actually just go like this, right, we've actually added the same bit of data multiple times to this analysis. And so that's the mechanism for doing it. But we need to update this value within this iterative loop that we've set up here for our analysis. So I'm going to use a counter. And every time point adder gets those 2 values written to it, I'm going to update counter, i.e. push it along one value, and then put it into add point. And I'll also clear my data set before I do that. And then if I print here, you can see I have 23 rows or points. We call them points, like a add point message here. And each row or point has 2 columns or 2 values. And these are the 2 descriptors that we generated. So we have dB and then hertz. And this is really useful. We could go and do some other machine learning on this. We could do tons of different things, but we're going to be plotting it in this 2-dimensional space. Again, I'm just going to find lots of little places where I've been quite wasteful with my real estate. So sorry about this. Just basically moving the patch up. What What you'll notice though is if I reanalyze 2 times in a row, or more, I keep adding rows to this data set. I don't want to do that if I reanalyze. I want to reset the data analysis here, and I want to reset the counter at the same time. So I'm just going to restructure my trigger up the top here. So I'll want to have a bang when everything's done. I'll want to start processing. And before that, I'll want to clear the data set. And I'll also want to send a bang to reset the counter. And so if I then have a look at all of that together, so we clear the data set and we reset the counter. And then I can put a bang here to symbolize the finishing of analysis. I'll change this to a print. Every time I click that button, we get the same thing because I'm clearing my data set and resetting my counter. And that's really important because, for example, if we want to change any of these parts over here, we'll always want to start from fresh when we add that data to the data set. And so, as I promised before, we might want to plot this data. And this is the fluid plotter object, which helps us deal with that. So I'll just put a little reminder, fluid plotter. And fluid plotter automatically, or not automatically, but it's designed to take the data from a data set and plot it. So if I make a copy of this, which has the same name, so they actually have the same underlying data, and do dump, and then have a look here. So dump gives us a dictionary of the values. I can then route dump and put it into the plotter. And now you'll notice that we don't actually see anything. This is because by default, Fluid Plotter plots on a range of 0 to 1. But we have data that lives between -22 and some other dB value that's lower, maybe -43 on one axis, and then 0 to possibly 20,000 on the other axis because it's in hertz. And so we can update here what it displays. So I want to do negative, maybe let's go with what I said, -60 to 0, something like that. And then on the y-axis, I want to do, let's say 200 to 10,000. And you'll see now that the points have come into view because we've set the domain properly. And what's really nice about the fluid plotter is that it gives us a readout when we click and drag of where we are in this space that we've set up. We're going to use these values to go and look up the points, which ones are closest to our mouse. And to do that more quickly, we're going to use a data structure called the KD tree, which is a very efficient data structure for looking up nearest neighbors, which is exactly what we're doing. We're looking up the nearest neighbor to our mouse. Particularly if you ever want to do this kind of thing in real time for a live performance, for example, having lots of points and doing a brute force search will be incredibly slow at some point, which could, interrupt your audio, your visuals, anything else. So KD tree makes for speedy queries on data, which is good for your CPU as well as, musical possibilities. So it's quite simple and straightforward to implement this KD tree within what we already have. I just tell it, hey, I need you to fit the analysis. And then we give it a buffer of data. In this case, I'm going to say your destination is called query. And that buffer is there. So when I do this and I mouse around, clicking and dragging, and I have a look in here, we see that that data is in the buffer. And then I say k-nearest query. And every time, you'll actually notice here, every time I mouse around, it outputs this message, buffer query. And if I send this to KD-tree, gives us the answer, the nearest point in this data set to the data that you provided in the query is 13, or identifier 13. Now, if you remember back to here where we did add point, some number point adder, this is the number that it was. So really, this is a slice index. This is saying the 16th slice, or the 20th slice, or the 15th slice is the one that is closest to your mouse. And we can take that value, route k-nearest, then we just get a symbol, which I can then convert to a number. When we can now play back slices based on the position of our mouse and the points that they're nearest to. And a handy little helper is the highlight message to the plotter, which will actually point out which point we are closest to. So if I say prepend highlight and just take it straight out of the identifiers and put it back in, you can see here that it's highlighting the point that we're nearest to. And so if I just have a mouse around, kind of makes sense. We have kicks down at the bottom and some cymbals or hi-hats at the top. But you'll see that when I track my mouse vertically, it seems fine. But when I go left to right, the matching is not quite right. Or what KD-tree finds to be the nearest is not quite right. And there's a good reason for this. When we add these raw values, KD-tree is doing a search in a Euclidean space. And it doesn't care that this is in dB and this is in hertz. A value of 1 is equal to a value of 1. So in this case, spectral centroid is weighted much more importantly in the search because the values are bigger. What we really care about is that on the left side of the plot, we have the lowest spectral centroid values. On the right side, we have the highest. And on the bottom, we have the lowest dB values. On the top, we have the highest dB values. Regardless of what they are, we want a relative scale. And this is called scaling our data. So we can quite quickly scale this data. And I'm just going to move this down. If I put it up here, I can say fit transform analysis to a new data set called normalized. And this is a bad spot for it. If I put it, if I make this a little smaller, that gives us some room. Perfect. And if I do this here, it says data set does not exist. So it's a good reminder that I need to make the data set here. So this is saying transform, fit and transform analysis to a new data set called normalized. It reports back that it did that. We change the KD-tree to fit around the normalized data. And we also are going to be dumping the output of normalized, not of analysis. And you'll notice all of the dots disappear because our range is in something much bigger than 0 to 1. So if I just use the range message, which sets both the X and Y range together, we get all our dots back. And you'll notice now that the mouse tracks much better in the space. And all the points sort of fill this normalized arena. If I print the output of normalized, you'll see the data has been scaled. We no longer have dBs and hertz. We just have values that exist between 0 and 1. So the lowest dB is 0 in this column here, and the highest dB is 1. The lowest spectral centroid is 0, and the highest spectral centroid is 1. And this makes both our plotting a little simpler. We don't have to know the range. We always know 0 and 1 are going to be the extremes. But it also fixes this problem of KD tree weighting a specific dimension much higher than the other, because now everything is relatively scaled. And if I turn my volume back up, it all seems to work. And so we can also change other parts of the patch. If I go for a very low threshold here, I get more slices. I then analyze. I then fit transform to normalize the data. I then fit my KD tree and dump. We get a different space. I'll turn it back up. And it makes sense. We have quiet values on the left with low spectral centroid at the bottom, and then high spectral centroid at the top, with those ones that are quieter being further towards the left and those that are louder being further towards the right. So there's obviously a lot of work here that we could do to clean this patch up. We could put things into little sub patches, which might help make the flow a little better. And we could probably automate all of these aspects, such as analyzing, normalizing, fitting the KD tree, and then dumping.